for the umpteenth time. What is our subject today? Well, it's measurement! Alright, so what is measurement? Well, before that, we need an intro to physics. Now, you've probably heard of physics many times, but many people acknowledge physics is something really hard. So people are like, physics equals hard. Physics equals genius. And sometimes, even the worst, physics equals useless, which is probably the worst of them all. So, that's why I wanted to come here and correct all of these things. Physics is not useless, physics is not hard, and physics is not genius. Now, I'm not sure where people would get the impression that it's useless. However, many people get the impression that stuff is hard or genius in physics because of all of the recent discoveries having to do with really complex stuff, like maybe quantum mechanics or black holes or other stuff you've never really heard of. And they're using these really advanced tools that you think are impossible to understand in order to find out their studies. However, with a step-by-step understanding, you'll be able to eventually reach the top as well. The reason that we are getting so intimidated is kind of because, what we are doing is skipping steps. We're trying to get directly to the hard stuff without acknowledging whatever's in the way. Also, that's one really stretchy leg, goddamn. So, we shouldn't be doing that. First of all, you're probably breaking your leg. And second of all, the kind of less important one, you're not taking everything step by step. And if you don't take everything step by step, you won't understand the final product. Alright, so there are a bunch of subjects in physics. Some of the main ones, and I say some, are optics, quantum mechanics, kinematics, dynamics, and there's also other stuff, like, for example, we have optics, quantum mechanics, kinematics, dynamics, electromagnetism, and others of that kind. Now, we're going to focus on these two for the beginning of our lectures, but we're eventually going to spread out from kinematics and dynamics, which both of those together form mechanics, which is the basic foundation of motion. Oh, and I also forgot relativity or gravity over here. So, let's say that, physics is actually everywhere. Because physics is not useless at all. Physics is actually everywhere in our everyday world. It's the thing we use to model everything that happens around us. It is literally built around the physical world. So you can't say it's not involved with the physical world. So, now let's say that you're a guy and you're playing basketball with some other guys. My drawing skill has improved a bit. So they're all dribbling in the court. One guy is hanging his head because he sucks at basketball, and the other guy is jumping on the goal. And this is the hoop. So this dude is literally flying. So here is the hoop, and you're doing this in like a gym. So now you have the basketball right now, and there's this one guy trying to steal it from you. And so what's happening over here is that you're trying to get it into the goal. So you throw it. And many things can affect the action of this ball. For example, it might hit one of the bystanders. But let's ignore everything that will not affect its motion for now. So we're only focusing on these things. These three things: the hoop, you, and the ball. Now there are many things that can affect the ball's motion into the hoop. Now, some of them could be color, the sound, the way and angle you throw it, its starting velocity, and a lot of other things. Now, there are a few that aren't really going to influence this thing at all, like sound or the color or the surroundings. But there are some that are fundamentally going to determine whether the ball gets in that hoop or not, like the angle or the initial velocity. So, that's just one example. And now, let's get on another example. Oh, by the way, say hi to my friend. He's right over here. So, now, let's say there are physics everywhere around us. Physics can be in optics. Well, okay, I already kind of described this. But let's say you were looking at the parts of a car. You wanted to know how they related to physics. Well, optics give you those nice headlights. Electricity is the stuff that gives you those nice headlights, or electromagnetism rather. Mechanics, wait, let's put EL over there. Mechanics is the stuff that's helping you move, but because of the friction that these wheels are exerting. And there are so many other places where we can find mechanics and physics as well. So now, one of the basic things in physics is measurement. Now, in mathematics, if you had, say, 97 plus 84, calculating real quick because I didn't have planned for this in advance, 170, 11, 181 would probably be enough. But what if, say, you were calculating using units, 97 meters plus 84 meters. You can't just write 181, you're not specifying the units. It has to be 181 meters. So, if you have the number 181, let's say, you say that your house is 181 from the store. Now, what would that mean? It wouldn't make sense to just say 181. It wouldn't just make sense to say 181 because that's not actually describing how far it is from your house. Sure, 181 sounds like a lot. But what happens when that 181 is maybe in inches? Probably typically wouldn't describe the distance between your house and the shop in inches, but I mean, who cares? This is an example. So 181 inches, well, 12 inches is in a foot. So 180 over 12 is 15. Thus, there are approximately 15 feet and 181 inches. And 15 feet isn't a lot. 15 feet, think 3 Sobornos stacked on top of each other. That's 15 feet for you. And I'm a very short guy, sat. So, that's the thing. It could be 181 inches. It could be 181 feet. It could be 181 meters. Or if you're living in a rural area or something, it could be 181 miles. Or if you're living somewhere far away in the Proxima Centauri system, could be somewhere far away in a star system that we haven't yet discovered, could be 181 light years away. So, that's the thing. The length really just depends on what unit you're using. So, now, the thing is, it's going to cause a lot of confusion if you're taking 2 units. But if you have calculations with 2 different units. So let's say you have maybe 2,559 centimeters or 2,560, just to make it a bit easier. And let's say you have 35 meters. How would you work this out? Well, let's first multiply 2560 and 35, which should be fairly easy. It's just basic multiplication. 5 times 0 is 0, 5 times 6 is 30, 5 times 5 is 25, plus 3 is 28. You carry the 2. 5 times 2 is 10, 12. And now you replace these. And you do the same thing with the 3. So you take 3 times 0 is still 0. Then you have 3 times 6 is 18. Carry the 1. 3 times 5 is 15. You add the 1, making it 16. Then 3 times 2 plus 1 is 7. That was incredibly boring, but who cares? So, that would be our answer. 89,600. But what units to put it in now? Well, how we say centimeter meters, because we were multiplying the centimeter and the meter. Well, that's really hard to interpret. So, what instead we could do is we could convert this. This could actually be written in just 25.6 meters. So, if we're moving the decimal point by 2 over here, then what we can do to convert this from centimeter meters into square meters is just move the decimal. And boom. And now, the reason we're using square meters is that we can convert this into 25.6 meters. Now, how does this work? Well, that brings us into the metric system. The imperial system sucks, don't use it. So, what does the metric system say? Well, here are some of the most common ones. So, there's the attometer. So there's the atto prefix. Let's look at prefixes just for a sec. So prefix, and we could say order of magnitude. I know I missed the A and misspelled magnitude horribly. Magnitude, but who cares? So atto, femto. Then there is pico, nano, micro, milli, centi, deci, and then we get to base. Then there's deca, which people spell with a K, which is weird. And then it goes up from there. So there's deca, and I believe there is, what was it again? Oh yeah. So there was a mega and a tera. That's all I'll write down for now. Tera is 10 to the 12. Mega would be 10 to the 6. Deca would be 10 to the 2, I believe. Or maybe 1. I'm mistaken. Base is 10 to the 0, which is also known as 1. And this is the base because 1 meter is just the length of a singular meter. It's the length of the base unit. Then you have deci, which is 10 to the negative 1. Centi, 10 to the negative 2. Milli, 10 to the negative 3. Micro, 10 to the negative 6. Nano, 10 to the negative 9. Pico, 10 to the negative 12. Femto, 10 to the negative 15. And atto, 10 to the negative 18. So, that is prefixes. And so, if we took, say, a centimeter, that's just 10 to the minus 2 meters, which we can also write as 1/100th of a meter, or 100th of a meter. So, okay, so those are our prefixes. Now, I want you to name some of the instances of stuff in your life having these prefixes on them. Now, oh wait, I forgot giga, which is to the 9. So this, and there's an exa, which is maybe 10 to the 15, I think. So those are all of the things we have over here. So when have you seen all of these in your life? You might have heard of pennies that are maybe 3 millimeters. You might have had a favorite radio show that was on 9.48 megahertz. You might have storage on your computer that's around 500 gigabytes. And maybe there are some doses that you've taken that maybe have micrometers on them. So I believe nanometer is this, and millimeters is that, so micrometers. So maybe there has been something you've heard of, like cells with nano on them. Maybe you've heard of technology with, I don't know, nanobots. Maybe you've heard of movies concerning things as small as nano. And pico is usually the small thing that everybody heard of. And all the rest is basically obscured in blackness because nobody knows about them. Alright, so those are the prefixes. You can study them while you can. Alright, so now in physics, it's super important to follow scientific method, creating a hypothesis, testing that hypothesis. And if your testing finds that the hypothesis is flawed, revise that hypothesis, test it again. And if it requires more testing, test that. And eventually, once you look like you have a feasible model, then it's good. So now, for example, let's take the example of Galileo. So, Galileo was like, let's say we had one object, maybe a cone for instance, that that's really heavy, like this Giancoli book, or this physics book, whatever. So, now, I'm going to ask you, which dump do you hear first if I drop these two? Alright, 5. Wait, you can pause the video for more time. 5, you can pause the video for more time. 3, 2, 1. Alright, now let's see which one hits the ground first. The dumps were around the same time. Let's test that again. But with some lighter objects this time. You go back, you freaking Giancoli. And boom. Now, let's say we had a stack of papers. I believe this is about 6 or 10. And you had one singular paper. Now, which one will fall to the ground first? You would think it's the same, but the stack of papers fell first. Why? Well, the reason that the stack of papers hit the ground first is that because the stack of paper, since there is so much paper, it negates air resistance. It's hard for air to press down and bend this thing. And it's hard for air to find ways to manipulate the movement of this paper. However, with one singular paper, that paper can wave and flap and be carried by the air. And so, that is called air resistance. And so, because there is air resistance, the singular paper wasn't able to resist the air resistance, while this stack of paper was able to resist the air resistance. And so, that's the reason. And so Galileo thought that was the reason. Okay, so Galileo thought that was the reason why this singular paper fell second and the stack of paper fell first. Now, the general consensus at the time was that if you had a heavier object and the lighter object, the heavier object would hit the ground first if you dropped them. However, Galileo came up with a logical fallacy that debunked this. He said you have a heavier one and the lighter one. Now, what happens if you take the heavier one and you tie it to the lighter one? Well, his hypothesis was that if heavier ones fell faster than light ones, that would mean that the light one would slightly slow down the movement of the heavy one. The heavy one would speed up the movement of the light one. So, in reality, it would be something like this. However, he also realized that together, these things would have more mass. So, if it really was true that heavier objects fell first and lighter objects fell second, then that meant that there were 2 ways that this thing could happen. And that was impossible because he realized that this thing itself would have more mass. And so it would drop faster, even though he previously thought that it would drop slower. So this fallacy proved to him that heavier objects and lighter objects fell at the same rate. And vacuum chambers weren't invented at all in his time. In fact, he was 6 feet under, hundreds of years before they were invented. However, he still made his hypothesis. And that hypothesis still holds true. We have found that out. We went to the moon and we tested it. And he's right. He is right, people. And so, that is all I'm going to say for today. So today, I kind of gave you an introduction to physics, something about the scientific method, and I believe the basketball court was over here. And that's really all I have to offer you. And, oh, wait, what's this arrow about? Don't talk about him. This is slanderous. I call for the arrest of whoever made that by the Espionage and Sedition Act of 1917. Alright, thank you everybody for watching, and we'll see you next time.
Brought to you by Brilliant.org.
Bari Science Lab to fall in love with math and science.